Well done. And thank you all very much for owning those scores. I really appreciate that. I tell you, people sometimes complain about my request to do that, but it's valuable for you to be proud of the scores. And remember, it's all good news. If you score, 70, 80, 90%, awesome. You only have 40 or 20% to work on. If you score 30, 40, 50%, awesome. You only have 50, 60, 70% to work on. So it is all good news either way you strike it there. Okay. So I appreciate you all taking those and owning those scores. That is all good news. And I will tell you as well, I told you before, the repetition of these quizzes is very, very important for you to drive this information home. It that repeating the quizzes again and again does indeed embed that information into your long-term memory. So you know it, you know the information. And I was telling you about the Effinghaus white paper that they have all kind of metrics in the study that he did, used a large control group, and overwhelmingly it supported the fact that repeating did indeed help the people to learn the information. His theorem that he came out with, it was called the forgetting curve. And he tracked it and gave good information on how it actually works. So good on all of you for owning those scores and posting those online. Good deal. All right, now, do we have any questions at all before we go ahead and proceed with our next lesson here? Okay, and don't be shy. If you have questions, jump in and let's get on with it. All right, let's dive on in here. Now, this next lesson goes over a particular area and a conversation that we'll have about cryptography in general. Now, this relates to, I remember I told you I was going to do a callback to and show how this stuff all relates in support of one of the three layers of the CIA triad. Cryptography actually supports the first two, confidentiality and integrity of information data, information systems data. Our data exists in three states of being. Your data is at rest, stored on some type of storage medium, a disk drive, tape drive, some type of storage medium. And if it's an electronic format, even better. And then we have the second state of being is in transit. Your data is being moved from one host machine to another host machine over some type of network connection. Okay. And then the third state of being is actively being used by we human critters. Now, in all three of those states of existence, our data can be now encrypted. Most certainly in the first two, while we're storing our data on a disk drive or some type of magnetic medium storage facility, and then in transit being transmitted across the network connection. Well, encryption is absolutely suggested in both of those states. Okay, and there's some very strong encryption algorithms out and available. Of course, there's still some older legacy ones that have been or cracked. The code has been cracked, so to speak. But the third state of being, while we are actively, for instance, editing a document or a spreadsheet or anything that we are actively working on in our computer systems, there are now some new co-processors, very high-speed processors that perform a function that's referred to as homomorphic encryption, or encryption while we are actively using the data. And it does it so rapidly that the data is not expressed in main memory in clear text format long enough for it to be stolen, because it just doesn't exist in that format long enough without outside of its encrypted format. Now, there are several different cryptographic algorithms and conceptual utilizations of encryption in general. Encryption, primarily, it's the same thing. We take clear text or plain text as an input, run it through some type of algorithm or encoding, and out of that comes what we call ciphertext or encrypted text. Okay. Now I'm going to step you guys through an exercise here I think that will help you get a little bit better understanding of how encryption actually works. Okay. Now, we're going to start with, you guys have to participate here, by the way. I'm going to step you guys through what I refer to as the old crusty dude encryption algorithm. Okay. It's a three-step process. I go through three passes of encryption. We're going to start with my first name, Doni. Okay. Now, the first step in this is referred to as obfuscation or a substitution algorithm. What we're going to do is to take each character of my first name and we're going to move backwards in the English alphabet 2 characters and substitute whatever you find. So if I'm moving backwards 2 characters from D, the first character there is going to be a B, right? And because I'm case sensitive, it's going to be a capital B. Now, you guys tell me, using that same algorithm, 2 previous characters in the English alphabet, what would be the other 3 characters? What is going to be their substitution characters that we put there in place of those? So the clock's ticking, and here's the music. There you go. MLG. Teal got to it. So we're substituting MLG. Now that's the first pass through the old crusty dude algorithm. Okay. Just a simple substitution character. Now the second pass through, we're going to use the output of the first pass as the input to the second pass. Okay. What we're going to do here is to go right past the first character in that. And I want you to pick out just 6 random characters off the keyboard. Doesn't matter what they are, but mix it up. Uppercase characters, lowercase characters, digits, special characters. But just pick out 6 random characters off the keyboard. And whoever gets to the chat box first, we're going to use your 6 randomly chosen characters. All right, Jorge got there. What is that? A capital G, an exclamation point. Is that an ampersand? Yep, an and sign, a 0, a $sign, and a lowercase d. That's a good one, Jorge. That's a really good one. Okay. So that is the output of the second pass through the old crusty dude encryption algorithm. The third and final pass, we'll use that as the input. And what we're going to do here is we're going to go right past the or right before the last character. Okay. And we are going to insert 5 digits only in descending sequence, and they don't have to be in order. 5 digits only, descending sequence. All right, 97654, what we got there. All right, let's do that. 97654. That's pretty good. Now, I'm going to ask you all what I call a lawyer's question now. And you all should be aware, a lawyer's never ask questions that they don't already know the answer to, right? In court, anyway. So the question is, if you look at this without knowing what the algorithm was, is there any way you can look at that and derive this from it? Well, I know the answer. No, you can't. Now, if I were to send you this text here, I would have to tell you what the algorithm that was used, or the shared key, so to speak, so that you would be able to decipher that and, in essence, reverse it to get back to the original input clear text. Okay. That's how encryption works. Now, the difference is the algorithms are more sophisticated. The information is scrambled up in different ways. Okay. But encryption is based upon the strength of the algorithm that is utilized to encrypt the data. and the sharing of the information, which is the key structure. Now, that particular form that we just did was referred to as a symmetric algorithm in that it was reliant upon a pre-shared key. Only had one key there. And I would have had to have shared that key with you in some out of bound mode so that you would know how to decipher the encrypted text. Okay. But all encryption is based upon some type of algorithm that scrambles the information that comes up. In some cases, they have them called hashing algorithms that create a set sized output regardless of the size of the file input. And it runs it through some algorithm and comes up with some pseudo randomly generated number, which is a unique identifier for that input. Okay. And then there are asymmetric algorithms, which is like your digital certificates. Digital certificates have two keys rather than a singular key like the symmetric or shared key algorithms. Digital certificates have a public key and a private key. Okay? And the two of those together are required to encrypt and decrypt the data. Neither of those, you can't derive the private key from the public key and vice versa. Here's the way that happens in digital certificates. And when you guys went to my website this morning, DonnieHelms.com, I would bet $1 to a donut that most of you have never been to that website before. It is a secure website. When you first fired up your browser, typed in the URL, DonnieHelms.com, it hit my website. My website then immediately sent down to your browser a copy of the digital certificate, which included the public key. Right? Boom, that hits your browser. First thing your browser does is checks out over the internet and validates that that digital certificate is still in force. Okay. The first thing it did was check in your browser cache to see if it already knew anything about that website. Probably didn't find it there. So somewhere out on the internet, probably at your service provider's servers, it found information there that gave them the IP address that actually hit DonnieHelms.com. And then when you receive the response from that, your browser then searched out over the internet and finally found the certificate authority that issued my digital certificate and said, yep, that certificate's still good. Then the public key that was sent down to your browser and the private key, which is still resident up on my server, the two of those negotiated the encryption algorithm that was going to be used for your session. Then and only then did it actually transfer the data. Now, when it validated that digital certificate, three very important things happened. The address line on your browser, most browsers do, all of them, not all of them do, but most of them, the address line turned green that says, yep, this certificate is good. The URL on the web address went https://DonnieHelms.com. And the little padlock that is on the top, typically on the top of most browsers, shows locked. That told you that you had encryption algorithms being enforced. Public key, private key had negotiated the encryption algorithm for that particular session, and you had a secure connection there. That is asymmetric encryption. Two keys, public key, private key. Symmetric encryption only has a singular shared key. Okay, that's the major difference there. Now, asymmetric encryption also is usually used for not large bulk data transfers, but for short bursts of data, like between your web browser and any website that is secure. Okay. But all of the encryption algorithms, whether they're symmetric or asymmetric, runs through some type of algebra. And that algebra scrambles the data, okay, mixes up the data, much like the algorithm, the old crusty dude algorithm, the three paths there. Okay. So, and there's different algebra that's used. Different algorithms are used to scramble the data. Some of them insert characters, some of them delete characters, some of them change characters with that obfuscation, substitution kind of thing. One of the oldest encryption algorithms, you guys may have read of it or heard of it, It was Caesar, Julius Caesar. They called it the Caesarian algorithm. And it was a simple substitution, much like the first pass of mine. And then there was an algorithm that was utilized in World War II as well called ROT 13, ROT 13. And they would type out the message of the day, and they would take each character in the English alphabet and move forward 13 characters and substitute whatever character it landed on. Okay. And that kept the German army, in essence, busy for almost 2 years before they finally cracked the code. And it was mainly because they didn't have as good an understanding back then of the English alphabet. Now every European child begins learning English in second grade school, so they got a much better grasp of it now. But that ROT 13 was based on the same concept of the Caesar's old encryption algorithm. Okay. Now, the key length of these encryption algorithms, the longer the key, the stronger the key, no doubt about it. There are some old encryption algorithms that use shorter, very uncomplex key structures. The latest version of this is referred to as military grade encryption, advanced encryption standard with a 256-bit key. 256 bits, very strong. That's 16 characters of data, 16 character keys and algorithms there. So very, very strong keys. Have to understand now, the longer the key, the stronger the key, but it also requires much more resources. It requires much more processing time, much more random access memory, much more CPU core time slice in general. And it has to run through multiple iterations in order to actually do the encryption and the decryption processes on both ends. Okay. So it's longer, stronger, but it's much, much larger key space that's utilized for those, for the processing, for the encryption and the decryption functions that are associated with using those large keys. No doubt about it. Okay. But it's very, very strong. Here's the asymmetric here. Now, asymmetric key structures are very long. Some of the very first ones here were somewhat weak, we'll say, but there was an organization that was three individuals, three researchers and developers, last names, Rivest, Shamir, and Adelman, were the three developers that created the very first company that successfully brought the whole digital certificate realm to the public. They didn't invent the technology, but they were the first ones to commercialize it. And that company we know now is RSA. They now create and manage digital certificates for organizations all over the world. And it is very strong algorithms, some of them all the way up to 248-bit key links. Okay. The cipher itself is very strong, and again, it's typically session level, and that's either session level, for instance, between excuse me, the example that I gave you, going to a website, okay, session level, short burst of information. We see at session level also data that's exchanged between two individuals, for instance, an encrypted email. Okay. We also see situations like, for instance, we talked about the secure shell connectivity. No, I'm sorry, we haven't gotten to that yet. But the secure shell connectivity, I'm confusing you today with you guys to a Thursday last week with my last team. The secure shell connectivity is a means of doing remote technical support on computer systems, and it uses an encryption algorithm where it generates a key and exchanges it with a target system as well. Now, RSA, the three gentlemen there, is what first created this company, but they utilize algorithms. It's called elliptical curve cryptography, ECC. That was formed by a couple of other researcher cryptographers, last names Diffie and Hellman. Also 256 or even longer key structures. And the elliptical curve cryptography is largely dependent upon in the algorithm using a minimum of 2 primary numbers in the algorithm. So typically very, very strong encryption. And I want you to understand too that regardless of the strength of encryption algorithms, if one has enough computing power and time on their hands, a computer can crack any encryption. It just may take decades or ages to do it. But with enough computing power and time, the computer can finally crack an encryption algorithm. Even the asymmetric public key, private key algorithms, those are susceptible to being cracked, but again, it may take a very long, long period of time. Okay. Now, hashing algorithms is a little bit different beast. Hashing algorithms is not intended to be unencrypted. They call it one-way encryption. Give an example of how these things are utilized. I run 3, 4, 5 different Linux distributions on various systems that I use and within virtual machines that I use teaching cyber classes. One of the distributions that I get the updates on that and any software that runs under it from a server that is up at MIT. Every couple of 3 weeks or so, I will get a message from the server that, say, well, we have this update to the operating system, or we have update to this application software that's running. Do you want to download that update? And of course, I always do. So what they do prior to encrypting, excuse me, the update file, the ISO file, they will run that file through a hashing algorithm that we both use. It's called the MD5 sum, Message Digest version 5. And it's a summing function. And it actually outputs a 128-bit unique number. Okay. And now that 128-bit is 64 characters. Okay. So I'm sorry, 128-bit is 16 characters total there. No, I'm sorry. Lost my little electronic mind there. 128-bit character string, again, it's not designed to be unencrypted. It is designed as a digital fingerprint of a file. And it doesn't matter what the size of the input happens to be. Take that ISO file and run it through this MD5 sum algorithm. Okay. It creates then basically a unique number identifier that defines a digital fingerprint or a signature for that file, that ISO file. Then they will encrypt the ISO file using their public key, private key. They will send me then the encrypted ISO file, which is my install file, and the MD5 sum function, the 128-bit key. And then I use the public key, private key to unencrypt the ISO, and then I run that file through the same MD5 sum function, and I create the digital fingerprint for that file. And in a little over 10 years now, those two digital hashes or that digital fingerprint have always been identical. Okay. So that tells me that that file was not intercepted in transit. It was not corrupted. There was nothing changed about it. That's that non-repudiation thing I talked about earlier when I was talking about the integrity of the file. I am assured that the file that they sent me is indeed the one that I received because I was able to recreate that same digital fingerprint using the MD5 sum function. Okay. But again, I don't decompile the key. I just recreate the same digital signature. They call those hashing algorithms, and it's a digital fingerprinting kind of thing. There's several of those. There's the secure hashing algorithm. There's 3 different versions of that. SHA-1, SHA-2, SHA-128. There's a couple of other ones that are used that are shorter key structures. There's RC4, RC5. That's also Ronald Rivest, the same Ronald Rivest that was at RSA. But it's a fixed length output signature, and it uniquely identifies a file. Now, if indeed it's a really weak digital signature, Some of them I've seen that are 64-bit. 64-bit's only 8 characters. Okay, any way you look at it, 8 characters. Well, a computer program may very well generate the same 8 characters or the same 64 bits um, with 2 separate files as the input because, with 8 characters, there's only 99,999,999 possibilities. Okay. So doubling that to the 128-bit, okay, that's 16 characters total. It gets almost exponentially impossible to create the same digital hash with different inputs. They call that data collisions, where you use 2 separate files, run it through the same algorithm, and it creates the same digital fingerprint. With shorter fingerprint, 6 character, 8 character, those data collisions are much more common. Once you get past the 10 characters or so, it's astronomical, the averages there that you will ever recreate the same one with different inputs. Just not hardly going to happen. So remember, hashing algorithms are used for doing error checking, digital fingerprint. They use them for what's called a cyclical redundancy checks or checksums. And it's used to assure and validate the integrity and the non-repudiation of information that is sent over network connections, not intended to be unencrypted. Okay. Digital signatures. There we go. And we use those are used quite a bit on emails. I have a digital signature and digital fingerprint that I use when I send encrypted emails to family, friends, and other assorted misfits. Also, when I'm distributing PDF documents that I want to assure are not copied, you can't copy it. Well, I'll attach a digital signature, a digital key to that thing. Without that key, they can't make any edits or copies or anything like that of that particular document there as well. So again, not intended to be unencrypted, but intended to be validated to ensure the integrity and the non-repudiation. Okay. So that's sort of a summary overview of cryptographic algorithms there. Remember a couple of things. The asymmetric encryption is 2 keys, public key, private key. Public key is typically distributed out into the wild, and you can't derive the private key from the public key, nor can you derive the public key from the private key. Both of them work together to do the encryption and encryption. And the first thing that most of them are doing nowadays with digital certificates is once they have validated, then they are used to create the session level encryption algorithm so that if somebody does have enough computing power and time to intercept message records and then decrypt one of them, well, that key can only be used for that particular session because it's dynamically generated on every session there. Okay. And then you have the symmetric algorithms, which is you have to distribute the key in some out of band mode. I mean, call them up on the phone. The key for today is, or encrypted email, text message, carrier pigeon, whatever way you get the secret key distributed out there. And that's one major thing about symmetric algorithms and encryption is you have to assure the security of the key distribution service. Now, in the asymmetric, the key travels along the same path that the data will, for instance, between your web browser and a secure website. Okay. So a little bit different beast there. Okay. Now, this lab, while fun, and if you've never done it before, it's a nice exercise to go through. Not going to answer any questions on your exam for you. Okay. Now, I mentioned the company RSA. I mentioned Diffie-Hellman, in the ECC type of encryption algorithms. RSA was the very first one that successfully brought this whole public key infrastructure concept to the public. They didn't invent it. Diffie-Hellman did with their elliptical curve cryptography, the ECC. But RSA capitalized on it, and now you've got a handful of companies that actually sell, service, and monitor digital certificates. RSA, Komodo is another one. VeriSign is another one. We see lots of private companies now or have begun to bring this whole digital certificate management, creation and management function in-house. It is a very hierarchical type of approach to the CA entity itself. CA is certificate authority. Inside the certificate authority, there's another downline entity called a request authority, an RA. So people make a request to the digital certificate company, and they say, well, we need to purchase a digital certificate to secure our website. Okay. So the RA gathers information about the requester, company name, domain ownership information, management information, technical support information on the domain, and other bits of attribute and property information according to the type of company that's doing the request. If it is a company that's going to be dealing in securities of sorts, they may do some type of securities credit background check, even criminal background checks in some cases. The certificate authority is an entity that must be trusted. Or, as I said, individual companies, if they're not using a third party CA, then they may very well create their own CA infrastructure internal and manage the whole thing inside. The Department of Defense does that now. They manage pretty much all of their certificate authority concepts inside. And any of you DoD cats, you're familiar with the CAC, the Common Access Card. Now those have evolved to a point that every one of the, well, I say every one of, most of them that are being issued now all across the DoD have a digital certificate associated with it. So when it's, swiped in front of a card reader or plugged into a computer in the computer labs, things like that, that digital certificate, public key, private key exchange is made there. And it's a validation and attribution that the user holding that card is a trusted entity in essence. So sometimes it's still performed by a third party CA. Sometimes it is performed as a complete in-house management function. There is a set of guidelines and standards called X.509, which is the public key infrastructure framework in essence. That was created by a couple of different managing entities and organizations. They created the guidelines and the standards that define the complexity of the key generation function. They define information about attaching attribute and property information to the certificate holder. It defines processes and procedures for the CA themselves, certificate authority, and the RA, the request authority, to do the background checks and basically cross all the T's, dot all the I's on all the information that is submitted requesting the digital certificate. And the hierarchy again is very important. Somebody goes to a company and says, look, I need to buy a digital certificate. Well, the RA will collect information about, again, names, address, telephone numbers, contact information, verify that the requesting entities say they're wanting to get a digital certificate for a website domain. Well, they validate that the requesting entity does indeed own and or manage that domain. With the information that goes in ownership, there's three basic bits of collections of information. There's the ownership, name, address, telephone number, email address, and so on. There's the managing entity, same thing, name, address, telephone number, email addresses. And then there's the technical support entity. Oftentimes, those are all three the same, okay? But they're still tracked and housed separately in the digital certificate database. So once all that information is validated and verified by the RA, the request authority, then they will package it all together. They will create the algorithm. The initial algorithm is going to be used for the encryption. They will create and assign the public key and the private key. And then all of that information is submitted upline to the CA, the certificate authority. Certificate authority basically revalidates all that information. And if indeed it accepts that registration or request, then it issues and digitally signs the certificate and then that certificate is sent out to whomever was the requesting entity. Okay. They then install that on whatever server or service that they requested the digital certificate for. Now, the digital certificate, if you'll notice here on this area of the screen, it's a large hexadecimal file is what it is, but embedded inside of that is the public key. The public key in the digital certificate, based on these cryptography standards, is then installed on whatever server the digital certificate was purchased for. Might be a web server, could be an email server, could be an application server. It could be a document server that's serving up PDF documents or whatever. So very specific types of certificates that are presented for these different types of installation functions. That, by the way, is where lots of organizations make mistakes. They'll purchase a digital certificate that is created for a web server and then try to install it on an email server, different configurations. Okay? So the misconfiguration oftentimes causes problems there. Now, the whole public key infrastructure thing is based around trust. The original certificate from a CA is what's referred to as a self-signed digital certificate. The certificate software then creates that very first root certificate, digitally signs it, self-signs it, and that root certificate then is utilized to create and digitally sign subordinate certificates or downline certificates, they're referred to, intermediate CA. In many cases, especially on the larger certificate authorities, once the root certificate is used to digitally sign and create the intermediate or subordinate services, they'll take the root certificate and server completely offline, lock it away in a lockbox somewhere, because that begins the root of trust. If that certificate is compromised, everything down line from that falls apart, because that is the root of the chain of trust that goes all the way back up to that original certificate. Okay. Excuse me. And then down line from the intermediate or subordinate servers, they all of those then create what's called leaf certificates, leaf like leaves on a tree. That is pretty much the hierarchy of the public key infrastructure. All begins with that singular self-signed initial root certificate. That's where the root of trust, the chain of trust begins, and everything downline from that all the way down. It doesn't matter if there are thousands of leaf certificates created. They are all dependent upline to that primary root self-signed certificate. Okay. Now, that's what happened. That's one of the reasons that the Department of Defense is now doing their own, because some years ago, there was an organization, not going to name them, but we'll just say they were in a different part of the world than we are. And they were responsible for issuing digital certificates to many different acronym government agencies: Department of Defense, NSA, Department of Homeland Security, DOD, MI5, MI6, security entities in the UAE and other governments all over the world purchased their digital certificates from this company. Somewhere along the way, somebody compromised their root of trust, their root certificate server, and the whole house cards fell apart. So that was when the decision was made to take that whole digital certificate management thing in-house. Lots of large companies are doing that same thing now. They're not going outside to commercial entities anymore. They're managing the entire thing in-house. The certificate signing request is what I was talking about, that the registration authority or the actually crosses all the T's, dots all the I's, and then ships that information upline to the CA. The CA then revalidates all that information. They sign and issue the certificate, and the information flows sort of downline from there, along with the public key, private key. It's installed out into the field. Now, all of these things as well are registered in the CA's database. Um, Many of the older ones now used to use what was called a CN identifier, CNID, common name identifier. Um, that has sort of, it's still there. You'll still find it in most of the implementations, but it's not the unique identifier anymore. There's sort of a serial number identifier that uniquely identifies the digital certificates to the CA database anyway. And then you will find that their main identifier now is called a SAN, a subject alternative name. And the thing that they've expanded the coverage on that, and I have this on my personal website. I don't have these subdomains active as of yet, but I will be activating them in the distant future. I've got student.donniehelms.com. I've got studenthelms.com, e.donniehelms.com, and then I have guest.donniehelms.com. All of those are actually fall under the purview of my singular subject alternative name digital certificate that covers everything. And most of the digital certificates now are set up that way so that they will accommodate existing subdomains and any others. They call it wildcard subject alternative name. So if the domain holder, creates 10 different subdomains, then one digital certificate will actually secure all of those down the line as well. Now, if indeed something falls awry with the digital certificate or the holder, if they fall out of favor for some reason, if indeed the digital certificate reaches its expiry date, and all of them have an expiry date that's issued. And I don't know, I guess it's different with the different CAs across the world. There are those that when the certificate goes out of the gate, it has a 48-month lifetime. But I've seen them with 5-year lifetimes. And I'm guessing that the user requesting it can go ahead and pay for an extended period of time. What you don't want to do is to use the same key structures on digital certificates for long periods of time. That gives the ne'er-do-wells, the thieves, thugs, and malcontents, that much longer to capture many more data frames while they're snooping and sniffing, and then gives them more possibility anyway of cracking your encryption algorithms there. Now, like I say, it's going to take a long time. It's going to take a lot of computing power to do that, but it's certainly a possibility. So you have to track that very carefully. Now, if your digital certificate's expiry date begins to approach, you'll start getting messages from your CA saying, well, you need to either redo the digital certificate or rekey it, I think is a possibility as well. Or it's going to expire, the certificate won't be good anymore. And then there are those that, if the company is found with criminal acts or violation of certain trade rules, things like that, certificates may very well be revoked. If they ever end up on the CRL, the certificate revocation list, they're there. You don't get them off of it. Now, you can get a new certificate if you want, but you're not going to breathe any life into the certificate that has indeed been revoked. The CA will house the information on their CRL, their certificate revocation list. And there's also query type language, they call it the online certificate status protocol. And it gives a real-time or near real-time updated information about the CRL, the certificate revocation listing from multiple locations all out over the World Wide Web. Once you hit the CRL, it's a dead certificate. You're not going to breathe any life into it ever again. But that's what your browser does when you first fire up a secure website. The website pushes down the digital certificate with its public key, and your browser then validates it. It sends out a query to one of these servers out on the internet somewhere. And if it's a large enough company and enterprise, they may even keep this CRL server in-house. Almost all of your internet service providers have servers and services that are aware of the certificate status on just about every certificate that's ever been put forth, except the ones that are in the private realm. But so you can get a pretty good update pretty quickly as to whether or not a specific digital certificate is still good in good standing or if it's been revoked for whatever reason. Okay. The life cycle of the keys on digital certificates, like I say, it's variable based on the certificate authority and the customer themselves. Okay. Um, the individual host machines that these certificates are stored on, not only do they have the copy of the digital certificate, they also house their private key. That private key is not shared out into the wild. So key management becomes an important thing there. Some organizations, especially those that manage lots of digital certificates, rather than having the key structures, spread out all across the individual machines that have the certificates installed only, they'll have some centralized key management function. And then the sites that have the digital certificate will utilize this specific messaging protocol, the key management interoperability protocol, they call it, in order to query back to the common key management service to see if indeed the key structures are still active, still valid, that kind of thing. So that key management server also may house a copy of the certificate revocation list as well. So it's a centralized type of key management service. And we see that a lot, as a matter of fact, in the large companies that are managing their own digital certificates. You'll see all of that consolidated into one in a large enterprises, one, maybe two server systems that manage the key structures themselves. And it uses that KMIP, that key management interoperability protocol, send and receive, process and message information from individual systems that are needing to validate the certificates, as well as users that are hitting those websites or email servers or application servers, whatever, so that those keys are managed in a centralized location. It also manages and keeps the owners of the digital certificates and those servers up to date as far as where your keys getting ready to or your certificate getting ready to expire. You need to do something about it. Here are your options, kind of thing. Okay. Now I talked about the homomorphic encryption concept. Okay. Homomorphic encryption is something that is utilized in a lot of different areas in computing in general, but it's primarily used to validate real-time use of information, and it gives we humans the illusion, anyway, that we're actually working on encrypted data. Now, it appears to be clear text to us on our screen, but these coprocessors or these processing function built in and utilize some of the cores in the multi-core processors. Well, it performs that functionality real tight in the central processing unit and highly protects the data while it is flowing in and out of the CPU and random access memory, by the way. There's another couple of things that actually utilize the secure enclaves, they call it. There is a whole umbrella type of it's not real. Well, I guess it would be considered like a framework, a security framework. It's called TPM, Trusted Platform Module. TPM now is supported by all of your major motherboard hardware manufacturers, the firmware programmers, and software vendors as well. It's very common nowadays for application software houses, the vendors, the people that write the application software, to digitally sign all of the files that make up their applications. Through this trusted platform module, which is sort of baked, it's a crypto processor that's baked into, there's a tie between the CPU and the motherboard and the firmware of the motherboard. When you install any of these digitally signed applications onto a system running TPM, and all of your modern systems support it nowadays, some of them come out of the box. It has the support, but you have to go into the setup of the system and turn that support on. Okay. Most of them now are just it's on by default. But anyway, when you install the application software that's been digitally signed, those digital signatures are then introduced to at the hardware level and stored at the hardware level when you first install these things. Going forward, then, anytime any of those digitally signed applications are accessed, whether it's system services or user level application software, those digital signatures are verified once again at runtime. And if the ones that is calculated when you access those files doesn't match the one that was stored when you installed it, well, those things don't get to run. That means that somewhere along the way, someone or something has corrupted or injured, as it were, the files that those digital signatures belong to, so they don't get to fire up and run. Okay. That secure enclave is an area in these in the motherboards themselves. When I load the digital keys up into that area, it's a protected area of memory. It's not accessible by application programs generally. Secure enclave is what they call that. Now, in some cases, there are certain systems that, because of the device itself, maybe a very small singular function controller or computer or something, or certain areas inside of operating systems that, especially virtualized areas, virtual machines, that are not secured or don't have the capability of wrapping security into their definitions. Sometimes we see these crypto processors or even sometimes external hardware that is wrapped around these individual functional components and provides the security for them. They call them hardware security modules, HSMs. We also have seen some of those in, there are certain type of networks that are spread out over a long distance. Hydroelectric dams, power plants, solar farms, wind farms, all of the individual components in those things have, sometimes dozens of little singular function computer modules that make them operate. And think about transportation. Out in the middle of nowhere down the train line, they have these little singular functional module computer systems now that do things like, slide the track over so you can offload a car on a side or rail or something like that. Well, those things typically, many of them operate with solar power. Many of them are, they do one or two functions. So they just simply don't have the processing power or the storage capacity to do any big time security algorithms. So they wrap these hardware security modules around them. And there's even certain ones that are considered tamper proof. And always makes me think of Mission Impossible. Somebody starts tampering with these things and they are actually self-destructive. This box is going to self-destruct in 5 seconds. Poof, it's gone. So that gives the functionality to network engineers and security practitioners to really and truly wrap some additional security wrappers around these things and reduce the entirety of the attack surface that's available to the ne'er-do-wells. Because, like I say, sometimes these things are out in the middle of nowhere, Nebraska, along a railway somewhere, but it is a launching pad into a much larger network. So they have to be protected. And those tamper-proof boxes there is one way of doing that kind of thing. Now, there's a concept here. Now, we don't see it. Sometimes the digital certificate company will provide this service by way of a third-party vendor. It's called key escrow. Sometimes companies manage this inside their own facilities there, according to the size of the company. But in essence, what it is the keys themselves, even older archive keys that aren't in active use anymore, but still could be used to crack and expose archives data as well. They're placed in the trust of a third party. And they call it M of N, many of a number of pieces. So they'll take a key structure. The key may be, let's say, 256 bits, okay, 16 characters, and some of them even larger, 32 characters, and so on, whatever the algorithm key might happen to be. but they'll carve it up into small digestible chunks so that no one entity has the entire key. They can't recreate it alone. They would have to have a number of the many different chunks and bring those all together so that they could indeed recreate the key. So that's called key escrow. They are backed up in secured format and distributed out across multiple trusted third parties. And you'll have to have, 3 out of 4 of those parties come together so that you might be able to recreate the fourth part of that key as well. That's called key escrow. And there's companies all over the planet that's their business. They house key structures, past, present key structures from many organizations and manage that for them so that those companies don't have to. Key escrow. Remember that term. May very well get a question about that on your exam, by the way. So that's PKI, public key infrastructure. It's very hierarchical. Remember the certificate authority, the CA, is sort of the top of the heap there. All of their business begins with that root certificate, self-signed certificate. That begins the chain or the root of trust. Downline from the primary root server, root certificate, is at least a couple of intermediate or subordinate certificate servers. They then are responsible for digitally signing and creating all the downline leaf certificates, which can go into the thousands. Many organizations, they will completely take the root server offline, lock it away in a lockbox somewhere, and then periodically, as the more intermediate leaf certificates are created, they will periodically, in a very secure environment, bring the root server back online and update its database with all, refreshing all the downline intermediate and leaf certificates. And then she goes back to sleep, in the lockbox again. The cryptography, as I said, it should absolutely be used in all 3 of the states of being as far as data is concerned now. Certainly data at rest, certainly data in transit, and for my money, data homomorphic encryption while we are actively working on data. Okay. You're going to find, I'll promise you, you're going to find from network engineers especially, you're going to get some pushback on using cryptography. And they sing the same old tired song. Oh, there's so much overhead. There's so much latency, so much time consuming programming, yada, yada, yada. As my dear old grandfather would say, that dog just don't hunt. I mean, because of technology advances, competition in the hardware world, competition in the software world, screaming fast dual core, multi-core, 16-core processor, CPUs, unbelievable massive amounts of random access memory, 1 gig, 2 gig, 10 gig network speeds, storage capacity, which is almost unlimited. Yes, there is still latency. Yes, there is still delay, but whereas it used to be measured in milliseconds and seconds, now it's nanoseconds and picoseconds. We simply don't notice it anymore. Yes, there is an initial setup issue, but once it's done, it's done. Then it just becomes a good, solid key management thing and digital certificate management. As far as overhead, it's just not hardly noticeable anymore. So don't buy into that. And think about along these lines. Those are all excuses, but no longer reasons why you should not do cryptography. The security gains you get out of using cryptography far exceeds any nanosecond delay you might encounter with using encryption algorithm, hands down. There are several different ways of doing encryption. I talked about the major difference in asymmetric and symmetric encryption being the, of course, symmetric, single key, 1 key, have to share the key, asymmetric, 2 keys, public key, private key. And the asymmetric encryption is better and more utilized for large amounts of data, bulk data. I'm sorry, the symmetric. Asymmetric is not good, not efficient at all for bulk data, short bursts of data. website to web page, or a browser to website. Now, large data dumps, bulk encryption, that's symmetric, no doubt about it. The issue there again lay in the secure distribution of the shared key. That's the main deal there. But by all means, encrypt your data, period. There is simply no better protection, and that's just one wrapper, one layer of protection. Now, what we're seeing in the digital certificate world now is quite an advance as well. In the old days, for instance, going from a web browser to a website, we used to use the digital certificates that were just considered SSLs, the secure socket layers. So the primary communication port from a non-secure website is port 80, HTTP protocol, Hypertext Transport Protocol. The secure version used to only just use the secure socket port 443. That's HTTPS, Hypertext Transport Protocol Secure. Now, all of your digital certificates, in addition to using the secure socket, they also use additional what they call TLS, Transport Layer Security. And that is implemented in a number of ways. One of the best, or one of the most effective, is what's referred to as tunneling protocols. Tunneling protocols is literally like drilling a little tiny diamond-headed tunnel through a granite wall, which is the internet. And envision it like that. Your workstation, website you want to talk to, internet is the granite wall between you. When you fire up that secure link, it drills that tiny little 5-micron digital tunnel through that granite wall that is the internet. So you got granite wall all around your connection. That's pretty good protection. But then it uses that secure socket, port 443, which is secure by nature, okay, already. So you got two wrappers around your connection now. Oh, and then we layer on the tunneling protocols, which is additional encryption algorithm that gives you the third layer wrapper around that connection through the internet, which is currently, anyway, the most unsecure environment on the face of the planet. Okay. So data at rest, data in transit, and data in use. Those are the three major modes of our data, or states of being of our data. And there is simply no real reason anymore, albeit you might hear lots of excuses as to why not to use encryption. Now, also in your database engines, and I'm talking about your common database management systems, the SQL databases, your Oracle database, Microsoft Access, Microsoft SQL, MySQL, and then there are blob types of databases as well. But these guys specifically, and I'm talking row, column, normalized data, what we're talking about here, built into the database management system itself, the DBMS, they offer certain types of encryption right down, in some cases, to the field level in the data. For instance, in most of your SQL databases, if I define a password field, there's no clear text data ever stored in that password field. It's used as some type of encryption algorithm, usually one of those hashing algorithms that we talked about earlier, and it stores the digital hash of the password, not the clear text version. Okay, so and that's very common in your SQL databases there. But it goes further than that. It even gives me the capability of encrypting an entire column of data, okay, which is a field. I can encrypt an entire row of data, which encrypts everything inside the database. Okay. And I can have algorithms that are running as part of my database setup. I can either program them myself, or in many of the databases, they have it basically you turn it on. So while the data is grabbed from the disk, it's encrypted. When it moves through these filters, it unencrypts it and hands it off to whatever application you're using to process the data. Page level encryption and decryption, they call that. Okay. So page level, record level, table, or field level, all of your modern databases will give you some form of encryption right down to the field level. Pretty clever. And it does it real time. You just simply don't notice the time lag anymore. Okay. Now, one thing about several of these types of functions, I mentioned the secure shell connectivity to a remote computer. I mentioned your digital certificate. I mentioned the symmetric keying algorithm, for instance, for exchanging encrypted files or encrypted messages or encrypted emails, that kind of thing. Now, in some cases, I need to, if it's a symmetric encryption algorithm, I need to share that key in some out of band mode. There is an internet based key exchange called IKE. I can, again, call them up, send a text message, send an encrypted email. Okay. Somehow I need to get that key to the opposite party because they use the inverse of that to decrypt the information. That is a major deal in using the shared encryption algorithms is how do I get that key distributed out into the field in a secure mode? There are certain key structures that I can utilize. I mean, internet-based transmission of those key structures I can utilize. Okay. Now, this is an interesting concept here, perfect forward secrecy. This was introduced as part of the RSA's digital certificate distribution methodology. And it's pretty interesting the way it goes. I want to read each of these steps to you because looking at it on the face value, it may seem very complex, but it's really not. Okay. We have two parties here. Well, three parties. We have Alice, we have Bob, and we have Mallory. Okay. Mallory is the hacker and attacker in this particular scenario. Okay. Alice and Bob agree on two values, P and G. And they share that information. They will tell you what the value of, in this case, P has a value of 23, G is equal to a value of 9. So in some kind of mode, they have determined that they're going to share those values among themselves. Okay. Mallory may even know those values right there. Okay. And then Alice, in this case, chooses a random number and keeps that number to herself. It's secret. And she doesn't share it with Bob. She doesn't share it out publicly. We're saying that number is A and that value is 5. Okay. Bob does the same thing. He comes up with his number and he keeps it secret. He does not share it out. His number is 3. Now, Alice calculates the value of her secret number, and then in the value there is an algorithm, G to the second power mod P, which is the one that was exchanged there with Bob, or her and Bob's number there. So she calculates that. Bob does the very same thing, and he uses that same G to the, what is it, G to the second, or G to the what power there? I can't see this stuff here. There we go. Okay. G to the B power, I'm sorry, not second, but B power. Okay. And he calculates the information based on those secret numbers that they both came up with. Okay. And then they transmit those calculated values. Okay. Bob calculates that, sends it to Alice. Alice now knows the A and the B value based on those secret values that they calculated. Okay. Alice calculates the value of that B to the mod P. And remember, they both know. I mean, she knows P, he knows G. They already got those. That's public information. But these other values here are secret. They're only known to them. Okay. And they're not known to Mallory either. So Alice calculates the value there. Bob calculates the value here. Okay. And then Alice and Bob have, by way of just using these same perfect forward secrecy calculations, come to the same secret value that generates the symmetric key. Okay. Mallory doesn't know it. She doesn't know the S or the G or the B. So she can't calculate the same perfect forward secrecy values because Alice and Bob have come up with their own secret numbers here that they keep secret, but they use as part of the calculations there that generate the entire shared key, symmetric key. Okay. So perfect forward secrecy is what that's called. And it's a means of, being able to generate a secret key, even though some of the values are known to the public at large. Okay. Now, I talked about the hashes, the password hashes. And I talked about that the password hashes are use a hashing algorithm to generate a key structure. Okay. Now, without, with short password hashes, 6 character, 8 character, okay, um, the 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 strength of that is what's referred to as low entropy. Okay, user generated using short keys, using just a computer program to brute force that. It's about people that use a 6 character key. There is only 999,999 possibilities it could ever be. Okay, only 6 characters. Okay? So a computer program could actually crack that wide open in a matter of minutes. Matter of fact, there's some older key structures on some of the older wireless access points were only 6 characters. There's code running around on the public internet now, the dark web, they call it, that can crack those things open in a matter of minutes. So what they've come about with is this salting or key stretching concept. Okay. Now, salting, you take the primary key structure that's generated by whatever algorithm is used by the hashing algorithm itself, and then the system itself then generates what we call a pseudo-random number to add to the end of that primary key. That's what I was talking about earlier when I was saying session level keys. That's what occurs there in many cases now. They'll have the primary key for the certificate that is the same forever, but this particular session, the algorithm generates that stretch or that salt that extends that key, but only for this session. Because the next session still uses the primary key chunk, but it may generate or it generates a different pseudo random number to tack on to the end of that key. Sprinkle a little salt on that key. Okay. Make it a little bit more appetizing there. And the key stretching is running taking the output from the first pass of a algorithm and running it through it again. So you're encrypting the encryption in essence of what it's talking about. And it also uses stretching algorithms. So the next time I run it through, I generate 2 more characters on the end of it. The next time I run it through, I generate 2 more characters on the end of it. So it's taking that key and stretching it out. And they usually do it per session. Okay. Now, don't get me wrong, those key structures still could be cracked as long as you got enough computing power and time on your hands. But it takes lots of computing power and time on your hands to do that. And let me give you an example. I have a defibrillator installed in my upper chest here. I had a heart attack back in 1997. I've never had to use the defibrillator. I'm one of those rare patients that does what the doctor tells me to do and don't do what they tell me not to do. So, but my doctor said it's sort of an insurance policy, right? Well, about every 6 months, I get a call from a young engineer down at their doctor's office facility down there, and he's like 23 to 24 miles away from me. And this unit here communicates dynamically with the bedside unit I have, and then that transmits data wirelessly through a WiMAX network to them. First time I ever happened, freaked me out. He calls me, he's going, Mr. Helms, yeah, we read the data off the bedside unit. Now I'd like for you to go and hold, there's a little handheld unit on that I hold over the device and it pulls all the information off and then transmits it to them. So we do that. He's going, looked at the data, everything looks sort of good. He says, I need to run a test now. So I'm sitting here 24 miles away. He says, okay, I'm going to speed your heart up now 3 different times. Speed up, slow it down 3 different times. I'm thinking, okay, then. So he does. And I literally feel my heart speed up. It's not uncomfortable or anything, but you can tell. And then it slows back down, speeds it up, slows it back down, speeds it up, slows it back down. And I'm thinking, wow, that is unnerving because all he's doing 24 miles away is pushing a slider on a console to speed up, slow it down. So I got to talking to him about it, and asked him, I says, well, what level of encryption are you guys using on that data? Because I know it's got to be encrypted. He's like, yes, sir. Said it is. He said it uses what they call military grade encryption. I said, is it AES 256 or AES 384? He says, oh, you understand this? I said, yep, I teach this stuff. So we had a nice conversation about it and everything. And I says, well, based on my thought here, it would appear to me that in order for a computer system to crack this code, that it would probably take a Cray supercomputer somewhere in the neighborhood of 40, 50 years to crack it if it were only working on that algorithm. He says, well, our estimates show, especially with the military grade encryption, that it would probably take closer to 75 years. So I told him, I said, well, young Jason was his name. I says, well, Jason, I said, then I guess the only person I really have to worry about is you. He said, yes, sir. Never really thought about it like that before, but that's about right. So that was quite unnerving, but they do that. And I asked him, I says, how often does it generate the key salt or the stretch? He said, oh, it's something, about every 27 to 30 seconds, that kind of thing. I said, okay, well, I'm not really worried about somebody cracking this code until we get to the quantum computing phase. Then everything changes. Encryption goes out the window if we finally get to past the theoretical parts of quantum computing. We shall see. Here's an interesting concept. Everybody's heard of blockchaining. Blockchaining is typically reserved to a blockchain type of network and used for cryptocurrencies, digital currencies. Blockchaining actually has a hashing algorithm. Each transaction or block that's generated in the network is used and hashed with the algorithm. It creates a hash copy. And then the next transaction comes about. It uses the hashing algorithm plus this block as part of the hashing algorithm to generate the next block and to hash the next and the next and the next. There is no centrally controlled or centralized ledger. The public ledger has every transaction that occurs inside the blockchain network. And if you want to solve the problems with elections being stolen, that's the way to do it, because it is 100% integrity check there. Because nobody can deny having voted. Nobody can deny they're not allowed to vote twice. We see it now used quite a bit in not just cryptocurrencies and digital currencies. We're seeing the blockchaining concept utilized a lot now. A lot of our encryption apparatus, I'm sorry, our security apparatus, like firewalls, intrusion detection systems, intrusion prevention, antivirus, anti-malware. Those things are pretty much dependent upon a signature database, but now the majority of them have baked in machine learning interfaces as well, which uses a similar concept to blockchaining in that it gets a data packet or a frame and determines the data points that is needed to use based on the signature database, and it creates a decision block for that. Gets another one that has different data points. Well, it uses that and creates another decision block. So it chains all those blocks of decision points and data points that it needs to check to see if there's an anomaly with the data packet. Okay. So blockchaining has got its place in the world. We'll see if it is actually being moved more into better control of banking, financial institutions, voting systems, things like that. And once again, if we get to the quantum computing phase, all that goes out the window anyway, so it's not going to really matter. The technique I looked at earlier when I was talking about the old crusty dude encryption algorithm, it's called obfuscation or substitution. Okay. There's several different flavors of that's used in all kinds of encryption algorithms. We see it used a lot in financial institutions, tokenization, masking of data, de-identification, taking out information that can be utilized to uniquely identify and or locate an individual. Substituting data with some type of a token. We've seen that with the asterisks in password fields, things like that. Also, masking data. A lot of folks don't realize most financial institutions are, by law, are not allowed to keep, for instance, your full credit card or debit card number stored in clear text format anyway in their database engines. They have to encrypt, and they'll only display usually the last four, maybe five digits in that. Steganography is what I was telling you about using embedding one file inside of another file, and they utilize image files, voice files, because for each character, each 8-bit byte in those, to generate a pixel on a screen usually only uses 3, sometimes 4 bits of an 8-bit byte. So sometimes there are 3 or 4 unused bits. Steganography software takes one file and utilizes those unused bits and hides it inside of another file. It's still, if you look at a JPEG with a JPEG viewer, it still looks like a JPEG. Very little effect on what the image or the movie or even the sound files encounter there when they use steganography software. So people use that to try to exfil data. They'll hide a file, a classified file or something inside of another file, sneak it outside, and then on the receptor end, the target end, they'll use the same steganography software to extract that file out of the carrier there. That's also how the ne'er-do-wells sometimes sneak malware into systems. They'll send somebody, oh, look at this beautiful picture of the or this video of the kitty cat chasing the light on the floor. When they open it up, yeah, the video plays, but they've also just released some kind of malware into their systems. Okay? It's called obfuscation, hiding something inside of something else, sometimes hiding it in plain sight, so to speak. Okay? So that's cryptography. Cryptographic solutions there supports confidentiality of our data. And like the hashing algorithms, the digital signatures also supports, in addition to confidentiality, the integrity of data, that non-repudiation kind of factor I was talking about. Several different encryption algorithms that are still in play and are still being used. There are older legacy ones that have been deprecated that simply aren't used anymore by organizations in general. In my humble opinion, you should use encryption algorithms everywhere. Most certainly in the first two phases of our data states of being, stored on some type of storage medium or being transmitted from one host computer to another computer. Okay? And there's so many different means of doing that. The key management is certainly a concern. The key stretching, key salting concepts, digital certificates are certainly something I would highly recommend for all publicly available websites, regardless of whether you're selling product or service or not. So that's cryptography of the different solutions that are available out there. And for me, it's a no-brainer. The security that you get out of using hashing algorithms for digital fingerprints or signatures and encryption algorithms for just protecting the confidentiality and of your data, the gains you get out of that are just insurmountable. No